Good. So I think I can probably start. Thanks everyone for joining to this new seminar from the Cambridge Ellis unit. Before we start, I would like to thank the sponsors of the Ellis unit. We are very thankful for their support of the unit. And today we have with us David Barber. He's a professor of machine learning at University College London. He actually studied at Cambridge. He got a degree in mathematics from Cambridge, and then he did a PhD in theoretical physics in statistical mechanics from Edinburgh University. He's currently, as I said, professor of machine learning at the University College London. He's a Turing Fellow, Ellis Fellow, distinguished scientist at UiPath, founding director of the UCL Center for Artificial Intelligence. He's director of Acidity in foundational AI at UCL, and he has co-founded several startups, including Reinfer, Human Loop, and Vectify. He works quite a lot on probabilistic machine learning, and today he's going to talk about training energy-based models. I'm going to stop sharing my slides, and David, you can share your presentation.
Great. All right. Thanks, everybody. And thanks, Miguel. So this is work that we did earlier this year, and it's going to appear in NeurIPS later this year. So I should thank Mingtian Zhang, who's my PhD student, just graduated, who's the main star here. He's done the majority of the work, but also thanks to Alex and Brooks as well. And yeah, so I think the main thing that we were interested in is the idea of training probabilistic models. And of course, most of us are very familiar with the idea of directed models, which have been kind of all the rage recently. And what I mean by that is that the model essentially is defined by a graph, and the edges on the graph are directed. So, for example, you might have, for example, a Markov chain, like here at the top, x0, x1, x2 to xt. And we're very used now to things like GPT style models and large language models and many others, diffusion models, etc., which are in some sense of this form with a Markov chain, or something more complex like something like a transformer, where you might have a BERT model, for example, that takes a sequence of inputs and outputs the sequence shifted by one. So next slide, please. But there's another class of models which are the undirected models. So in this case, if the graph doesn't have any directionality to it, and it's just defining some distribution in some way over these, say in this case, 4 variables. Now, of course, we can also introduce structure into this distribution as well by not having edges between some of the variables. But in general, we're interested in this, this class of defining these undirected models. So there's no particular sort of direction in terms of which the distribution is represented. So next slide, please. So one way to do this is to parameterize this distribution in the undirected sense using something like a deep neural network. So for example, we might have those 4 variables, x1 to x4, and we might put them through something like a deep neural network. And at the output of that neural network, eventually we'll have a scalar value, we'll call that, say, E. And how does this define the distribution? Next slide, please. Well, we could say that the distribution could, for example, be the energy might be, say, the exponential or something like that of the negative of the f theta of x. So in this case, f theta of x might be, say, the output of the neural network, and we then just exponentiate it to get something positive for the distribution. And this q theta of x then would define our model, and we'd like to fit this to some training data. So here, z theta is the integral of the exponential of the negative function. And the challenge here is that typically this is going to be difficult to calculate. This normalization term for most functions f will not be known. I should also say that we are restricting our interest here to the case of continuous X. The case of discrete X is something that maybe I can discuss at another time, but in this talk we'll focus on the continuous X situation. So in some sense, this is a very general framework for modeling complex distributions, but it has some huge challenges. They're very difficult to train, and they're very difficult to sample from, or pretty difficult to sample from. So how can we make progress with this? Well, one of the probably the most widely used approaches is the so-called denoising score matching approach, which we're going to discuss in a minute, actually doesn't really do quite what you want. It doesn't actually learn the correct underlying distribution, and theoretically is not guaranteed to do the right thing. So next slide, please. Okay, so let's go back to basics. What we'd like to do, we'd like to, given a training data set, x1 through to xn, and these are samples from some underlying distribution PD, we'd like to fit this to the data, or fit the model to this data. And one way to think about that is to minimize the KL divergence between PD and Q theta, in this case, our energy-based model. So up to some negligible constant, this is the integral of PD with respect to log Q, and we plug in the form of log Q, it's this exponentiated negative function, and we're going to get then this term here. So this is composed of two terms. There's an integral and expectation. The first term of f, that's no big deal, but the second term, log z, is going to be difficult. This is not tractable typically for this energy-based model. And there have been a variety of approaches over the years that have looked at how to address the difficulty of estimating log z. Okay, next slide, please. So one approach is to think about the Fisher divergence. So this is defined as a divergence between two distributions, which is defined this way. The PD is the data distribution, in this case, Q theta is the model, and it's this expectation with respect to the data distribution of the score function of the data P, D, and the score function of the model Q theta. So what is the score function? It's the derivative with respect to x of log P of x. So why do we do that? Well, it's useful because if you plug in our energy-based model, the score function will not be dependent directly on z. So, the score function is just then essentially the gradient of the function value x, and z has disappeared. So we don't need the normalization. That's the good news. The bad news, though, if we look at the Fisher divergence, is that we need the score function of the data generating mechanism PD. And we don't have that. We only have samples from PD. So we don't have an explicit representation for the score function of PD. So we don't know what to do with that term. Okay, next slide, please. So one sort of, by now, I guess, classical approach is from Albert Hiberinen. And what he showed is that you can rewrite this Fisher divergence up to some constant in the following way. This is again an expectation with respect to PD. But if you look at the corresponding remaining expression there, we only have terms which depend upon the model Q. Okay, so there's a score function of Q in both the first and the second term. So this is a very interesting approach because we now can actually calculate this Fisher divergence up to some constant, and we only need samples from PD. And this has been very useful and very popular. But there's a challenge here, which is that if we're doing training, we need to calculate these derivatives of the score function actually essentially at every single parameter update. So we need these second derivatives to evaluate this approximation to the Fisher divergence, and we need to do that at every single parameter update. Now that's going to be really tough if we have a very high dimensional X. Yeah, so let's go to the next slide, please. So we're interested in other ways to approach the challenges around the Fisher divergence. So I'm going to take a slight detour for a minute or two, and I want to talk about something slightly different, but it's going to be heavily related. So let's imagine that you've got, say, two distributions, in this case, P and Q, and let's say they're delta functions. So there's only mass on point A in P and mass on point B in Q. And let's imagine that you wanted to calculate, for example, the KL divergence between P and Q. Well, that unfortunately is not well defined here because the supports of these distributions are not overlapping. So actually, log P over Q is ill-defined. So that's a problem. So you can't calculate the KL divergence between these two distributions. Next slide, please. So indeed, more generally, you can have a divergence D between Q and P that isn't defined because of, for example, mismatching supports. And is there a way to sort of heal that, make it better defined in general? Well, one way to do it is to define what we call the spread distributions. So we define, if you take your original model, say Q or distribution Q of X, we're going to define a new distribution Q tilde on X tilde by integrating the distribution, sort of smoothing it, if you like, with respect to a Gaussian distribution. For example, it doesn't have to be a Gaussian. And similarly, we define P tilde of X tilde to be, again, the integral with respect to some kernel or some smooth distribution K X tilde given X, again, of P of X. Okay, so the Gaussian in this case would be one option, because there's a minus sign missing in the exponent there, exponential of negative X to the minus X squared. But in general, what we want to do is to define some distribution such that the Q tilde can be represented then as a convolution between some smoothing distribution or kernel K and the original distribution Q. And similarly, because we're using the same kernel, P tilde would be, again, the convolution between that kernel and the distribution P. So if you choose a Gaussian distribution, this has support everywhere. So what that means is that the divergence between the smooth versions Q tilde and P tilde is always defined. And indeed, you can show that if the divergence between the smooth distributions is 0, that of course implies not just that Q tilde is equal to P tilde, but that actually Q is equal to P. Next slide, please. So you might wonder, why is this true? Well, actually, it's a very simple argument. So if you think about, again, going back to the definition of Q tilde and P tilde, they are written as convolutions. So indeed, that divergence, if it goes to 0 between the smooth distributions, that implies that Q tilde is equal to P tilde, which also, if you take the Fourier transform then of both sides, tells you that Fourier transforms must also be equal. But because it's a convolution, the Fourier transform of the convolution is the product of the Fourier transforms. So the Fourier transform of Q tilde is a product of the Fourier transform of Q, transform of K. And similarly, F, the Fourier transform of P tilde, is a product of Fourier transform of P with the Fourier transform of K. So if you choose a convolution or a kernel K whose Fourier transform is strictly positive, that means that you can divide both sides by F of K, and you end up with the quality that the Fourier transform of Q must match the Fourier transform of P. And because that's invertible, that implies that Q must equal P. So that's a kind of a general approach to, if you have a divergence which is not well defined, you can make it well defined by doing this this convolution, essentially, with some kernel whose Fourier transform is strictly positive. Okay, next slide, please. So the graph of that would look a little bit like this. These are the smooth distributions, but indeed these only a match when the original distributions, in this case the delta functions, match, and that must happen when A is equal to B. So if you think about the delta situation, actually when you do the smoothing, you're going to transform a delta function into a Gaussian. So you just got the difference between two Gaussians, and of course they match when the means are the same. The widths would be, the variances would be fixed. So they must have the same mean, which means that A is equal to B. Okay, next slide, please. Okay, so that was a little aside. That's the idea of how to define a smooth distribution. So let's go back to the idea of the denoising score matching. So what we're going to do now is we're going to define a smoothed data distribution. So P tilde of D, which is going to be defined through, again, this sort of kernel, this convolution, if it's a Gaussian, with the original data distribution PD. And similarly, we're going to define a noisy model. So Q tilde is going to be defined as an energy-based model. And now we're going to go back to the Fisher divergence and think about how to define that quantity. So we could say the Fisher divergence would be the expectation with respect to our data distribution. So that should be P tilde of D here. Again, the score function, the difference between the score functions of the two distributions. But now, actually, the score function of the noisy distribution with respect to the derivative with respect to x tilde is well defined. And you can show quite simply up to an additive constant that the Fisher divergence is equal to this expression here, where now we have a known value for this score function for the noisy distribution, and we have original score function here. There's a plus here, which is related to if we just actually do the calculation. But the good news is now we have an explicit representation for the score function, for the Fisher divergence in terms of the score functions of Q. So next slide, please. So this is actually nice. So this is not a new thing, but so the challenge here is that if you were to learn this model, right? So you'd fit, say, theta to minimize this Fisher divergence, and let's imagine you're fortunate and you can actually drive this Fisher divergence to zero. What does that mean? Well, it tells you that the noise distributions, for example, P tilde is equal to Q tilde, so they match. But the problem here is that PD is not the same as P tilde D, right? The noise, you've actually noised the distribution. So all you've ended up doing is fitting your noise distribution, your model to the noisy data distribution. You've not fitted to the actual data distribution. So one common thing that people do is they take this variance of the Gaussian distribution and they shrink it towards zero during training in order to try to encourage the model to actually learn the data distribution rather than the noisy data distribution. Now, the challenge there is that as you anneal the sigma towards zero, this causes numerical problems, and typically the resulting optimization becomes unstable. So that it doesn't work, in our opinion, super well. So what we are going to do instead is try to find another way to retrieve from this Fisher divergence between the noise distributions the actual on-noise distribution to do it correctly without annealing sigma to go to zero. Okay, next slide, please. All right, so the idea is that if we, for example, can drive the Fisher divergence to zero, and so that our Q tilde is matching the noisy distribution P tilde, then there exists a unique underlying clean model such that the noisy Q is the convolution of the clean model Q with the kernel P, x tilde given x. Okay, and if we can do that, then actually the Q will actually match the data distribution PD. So in other words, we want to try to define, given a learned Q tilde, we want to try, and we know the noise distribution Px tilde given x, we want to try to identify a Q such that Q tilde is equal to the convolution between K and P, between Q and P. Okay, so that's the idea. Now, directly finding that Q to satisfy that equation is also very difficult. We don't have a direct way to do that. So what we're going to try to do is actually quite a sneaky thing. We're going to try to sample from a joint distribution to actually then recover a sample from the clean distribution. So this joint distribution is defined to be the product of the noise distribution px tilde given x, which we know, this is a Gaussian distribution, and the Q distribution, right? This is going to be the clean distribution. Now, we don't know this Q distribution, so it's a slightly complex argument, but the idea is that we're going to try to define this in a way, and then we're going to run Gibbs sampling. So in other words, we will fix x and sample an x tilde. Well, that's okay, because that just requires x, given x, we sample a noisy point x tilde. And then we'll switch, we'll say, okay, given x tilde, we want to define a sample from distribution x given x tilde. So we need to know what that is, right? So how do we get access to the quantity p of x given x tilde? And what we're going to do is we're going to define a Gaussian approximation to p of x given x tilde. And in fact, we're going to define the exact Gaussian distribution. In other words, if you were to match the first two moments of p of x and x tilde, we'll find them analytically and we'll define a Gaussian distribution based upon those first two moments. So once we've done that, we'll have a Gaussian approximation for p of x given x tilde, which we could then use within a Gibbs sampling scenario to then iteratively try to sample from both the noise, but actually the clean data distribution as well. Okay, next slide, please. All right, so the way this works to find this, this analytical approximation is we're going to start from a result a couple of years ago. I'm not going to go into the details, but if you write down our constraints that we want given q tilde, and we know p of x tilde given x, and we've got this, we want to try to find q that satisfies this equation. If you take the derivative with respect to x tilde of both sides, you can show, Song and others showed a couple of years ago, that actually the average, the mean of this distribution p of x given x tilde can be represented as x tilde plus sigma squared times by the score function of the q tilde distribution. And you can call that, also say x mu of x tilde. So this is a very nice result. You have an analytic expression for the mean of this, if you like, posterior distribution x given x tilde, directly in terms of the original score function, or the score function of your learned noise model. And it's interesting to note that if you were to plug this back into the Fisher divergence, again up to a negligible constant, you can write the Fisher divergence actually as a function of the difference between the it can be directly expressed in terms of this mean function. So in fact, this mean function essentially contains all the information you need to fit the distribution itself. Okay, next slide, please. All right, so the Gaussian distribution has got two things. It's got the mean, which we now define, which was also figured out a couple of years ago. And then we need also though to calculate the covariance of this distribution. So last year, Bao and co-authors analytically derived one approach to doing this. And I think this was a best paper. I had a best paper award, maybe at ICML last year, I can't remember exactly. But anyway, but what, that was a very interesting paper, but it's got a severe limitation in the sense that the covariance that they derived does not depend upon x. So we're looking at p of x tilde given x, and actually the covariance for x tilde does not depend upon x. It's also isotropic. So it's a Gaussian under the restriction that it's not x dependent and it's actually isotropic. So that's actually quite a severe limitation. They do derive an analytic expression for it, but it's quite restrictive. So what we showed is that if you go back to that constraint that q tilde is equal to the integral of p of x tilde given x times q of x, and you to differentiate it twice, and I won't go through the mathematics here, you can actually derive the following expression for the covariance of the distribution p of x given x tilde. And it's given by this expression here. It's actually, again, a simple expression in terms of the score function itself. Okay. So what that means is that the exact analytical expression for the posterior distribution can be expressed in this way, again, using directly the original learned Q tilde distribution, your noisy Q tilde. So just to go back, to step outside a little bit, what have we achieved here? We've now defined the Gaussian for the Gibbs sampling situation. So we can start off with, for example, some x. We can sample an x tilde, then we give an x tilde. We can sample an x, and we can iterate this until a certain number of Gibbs sampling steps. And then once we've got that, we could say, okay, let's look at the final, say, x that we have after a certain number of Gibbs sampling steps, and that will be a sample from the clean underlying Q distribution. So this is an alternative way to essentially fit distributions to these energy-based models based upon something like the Fisher divergence, but without using the annealing approach. Okay, next slide, please. All right, so does it work at all? So just to give you some toy problems, here on the left is some true data. This is for mixture for Gaussians here. And if you look at the, say, the B column here, this is using a sort of a slightly more complex, so a learned diagonal distribution for the approximation of the Gaussian in this Gibbs sampling scenario. That's one that is being learned numerically. You can actually also analytically figure out, this is from Bauer's paper last year, what is the analytic approximation for this isotropic X-independent approximation, and these are the samples that you get from the learned clean distribution Q. And this is what we get on ND using our analytic full Gaussian approximation. So that's obviously a slight improvement on the previous two things that have been done in previous years. And you get a similar result for example, this spiral data on the bottom row as well. You find that our approach is actually also doing a little bit better than the previous approaches. Okay, next slide, please. All right, so going slightly beyond very, very toy model to another slightly less toy model, our fantastic MNIST data set. Here I can't remember the exact details of the model, but we've defined an energy-based model using something like a unit architecture, and then we map this down to a scalar value to define the energy function. We do this noisy Fisher divergence approach. We then calculate these analytic expressions for the Gibbs sampling. And then what we do here on the top row is we start with just a Gaussian random noise sample. So that's, say X tilde, and then we sample X, and then we sample X tilde. And this is what we see going through the stages here on the top row. So we then sample, say, an X, and then X tilde. And I think actually, maybe we're not showing the X tildes here, we're just showing the X's as we go through the various stages of Gibbs sampling. And what you can see is that starting from this random noise, we start to coalesce around things which actually look like the original MNIST data samples. So that's actually quite nice. And if we were to compare, that's our approach. But if we compare this with the previous approach, for example, from Bao last year using this isotropic X-independent covariance sampling approach, you can do a similar thing, but the samples are not quite as good as the ones that we get. Okay, next slide, please. So I guess the obvious question is, can you go beyond these slightly trivial problems to higher dimensional problems as well? And the answer is, to some extent, yes. So we applied it in this case to cell lab A, again using a similar unit architecture, and we then sampled faces using this Gibbs approach from the model after it's been trained using this Fisher divergence approach. And I think, these are not too bad. They're, reasonable samples of faces. Are they state of the art? No, not yet. But it's, it's kind of, it's not too bad. It's kind of quite reasonable. Okay, next slide, please. So in conclusion, what we've done here is we just remind you, we're interested in training these energy-based models, and they're interesting because in some sense, you can define very long-range dependency between the elements of the distribution, and there's no direction bias. And it was, an extension essentially of the score-based approach. And we showed how to essentially heal that to enable you to actually define in a kind of in a well established way samples from the original on-noised Q distribution, and that was through this analytical approximation of the Gibbs sampler. And we have reasonable results on small-scale problems. And just to say a little bit, I think some of you are probably very familiar with the idea of diffusion models, and I hope that you can see some hints of the connection here with diffusion models, because as you see through the Gibbs sampling stages, essentially what's happening is you're having an iterative denoising of the original sort of the starting point, the purely random noise for the sampler. And mathematically, there are some actually very deep connections between the diffusion model and what we're doing here, and we will try to tell you more about that in future work. So I'll leave it there. Thank you very much.
Good. Thanks a lot, David. We still have time for some questions. If anyone wants to ask something, feel free to write any questions in the chat. And in the meantime, I can ask one question. Let me see, because I am looking at the chat and the slides at the same time. Sorry, let me share the slides. So maybe I can ask one question. One thing that you have mentioned is that you do this Gaussian approximation. And you mentioned, I think, here precisely that you have the optimal Gaussian approximation. Could you give a few details in what sense this is an optimal Gaussian approximation? The way I understand is that it seems that it's because you are approximating the moments. Is that right? But
yes, that's right.
The true distribution will be different. Maybe I can go back to the slides. Yeah, I think it's this one. No, basically.
Yeah, that's right. So the work from Song showed they can calculate the exact. This is an exact expression. So the first moment of x given x tilde is given by this expression. So that's of course you're right in the sense that the p of x given x tilde is not necessarily a Gaussian distribution, right? It has non-Gaussian properties in general, but you can calculate analytically. You can calculate in this case the first moment exactly, right? So there's an analytical expression for the first moment. And what we showed is there's an analytical expression for the second moment. So if we then do moment matching, which is given here, so if we then say, okay, we'll fit a distribution to those first two moments, and we choose that to be a Gaussian, then we can proceed that way. Actually, it's also possible analytically to calculate the higher moments as well. So you can go, to third, fourth moments as well, and derive analytical expressions for them as well. We haven't done that, but of course then you have to think about what distribution class you want to fit to those moments. But also the computational cost increases as well. So one thing I didn't mention is that perhaps if you look at this expression, for example, you'll see that the mean depends upon the derivative with respect to x tilde of the fitted q tilde distribution, and similarly the covariance depends upon essentially something like the Hessian of the fitted q distribution. Now, this is expensive because x tilde is typically very high dimensional for the kinds of non-trivial problems we're interested in, like say fitting images. So calculating these derivatives and Hessians, and actually you'll need Hessian gradient products in general, is actually quite demanding. We don't have to do it during training, right? So this is different to the original work that Hivarinen was doing, because during training, you needed to calculate these gradients with respect to x tilde of q tilde, and similarly Hessians of second derivatives with respect to x tilde of q. We don't need them during training, but we do need the second derivatives of q tilde during inference, right? So inference here is a little bit slow, but yeah, in principle, yeah, it's to answer your question again, yes, this is the moment matching Gaussian, optimal moment matching Gaussian.
Mm-hmm. Good. Let me see if anyone has other questions. Maybe I will ask one last question. So when you train diffusion models, you're always adding this amount of Gaussian noise, and you mentioned that the people take this limit where the sigma will go to 0. Does this approach allow you to maybe counteract then that effect that basically you have to have like some positive sigma value during training, and maybe through this approach you can kind of remove that? Could you basically explain it also in that way?
Yeah, so this is a little bit more I guess the art rather than the science, to be frank. So if you think about I mentioned this idea about smooth distributions, right? So I said, okay, if we think about, for example, two delta functions and you can't define the divergence between them, for example, KL divergence, and you can smooth them with respect to, say, some amount sigma squared and some amount of noise sigma squared, then in that particular case, no matter what amount of sigma you use, in principle, you have to be bigger than 0, otherwise you're in some numerical trouble. But for any reasonable amount, big enough that your computer doesn't run into underflow problems, any sigma will do, in the sense that the minimal of that minimization of that corresponding objective will result in A equals B, in other words, P matching Q. Now, in this particular case, in the energy-based model, things are more complicated, partly because our Gaussian is only an approximation to the truth, right? The true posterior distribution, Px given x tilde, is not a Gaussian. So we're doing, in some sense, an approximate Gibbs sampling step. And that approximation then will be affected by the value of sigma that we're using. And so there's not, in some sense, a direct way to say, well, what's the optimal value of sigma to use within this Gibbs sampling approximation, or this approximate Gibbs sampling approach. So for that reason, this is, it's a little bit more of an art than a science. We choose a sigma squared, which we experiment with different values, and we choose one which seems to work empirically reasonably well. So this is perhaps a little bit analogous to the idea in diffusion models of the annealing schedule. You also have a choice there about how to decide what sigma is, and you can also do a similar thing. I've not talked about it today, but you can obviously a natural extension for the work that I presented today is to think about doing multi-stages, where we don't just say add a single amount of noise. We can do this at multiple levels and actually define something that looks more similar directly to a diffusion models. And then again, then you've got the choice as to what that level of noise should be, and we play a little bit with that to get good empirical results. But we don't have, at least I'm not aware of us having a really justified, well-meaning mathematical way to set the value of sigma squared, and the results do depend upon the setting of sigma squared.
Good. Thanks a lot, David. Thanks a lot for joining. I think we need to move on to other things, but yeah, let's thank you, and hope to see you soon in another event.
Great. Thanks, everybody.
Bye. Bye.
Bye.